Welcome, my friends. 2 exhausting weeks lie behind us. The content of lesson 12 and especially the problem set were pretty tough. So in this week's lesson we are going to relax a little bit. We return to homomorphisms, and in this week's lesson I'm going to tell you what the kernel and the image or range of a homomorphism are. But for this we absolutely need the stuff we did in the last 2 weeks. Now phi is, as always, a group homomorphism between groups G and H. I do not write down let G and H be groups, but it is understood in this notation. If we write that, we mean a group homomorphism. Now its kernel is defined as the following set. The abbreviation is Ker-phi, sometimes capital K, sometimes parentheses around the phi, but I like to keep notation as light as possible. So the kernel is a subset of the group G consisting of all the elements of G that get carried to the identity of H under phi. So in the terminology of the last lesson, this is nothing but the fiber of the neutral element or the identity of H, the pre-image of the singleton set E sub H, so this means exactly that. All the elements that get mapped to the identity. Then we have the image. This is simply the definition of the image of a map. This has nothing to do with being a homomorphism, whereas this here is especially designed for homomorphisms. We are going to see why in a minute. So the abbreviation I use is im-phi, which is nothing but phi of G. So I plug in all the elements of G into phi and I end up with this set here. All the phi of lowercase g, G element of G. And again, this is the definition for any map between G and H. Sometimes the word range is used with this abbreviation, but I'm going to stick with im. Okay. Now, an elementary but very important proposition, proposition 16. For a group homomorphism between groups G and H, the following holds true. First of all, the kernel is always a subgroup of G, so this set here is a subgroup of G, and the image is always a subgroup of H. This is the most important property here when talking about the kernel. The kernel shows me when a homomorphism is injective. The following is true. Phi is injective if and only if the kernel is trivial, meaning it consists only of the neutral element of G. So a very useful criterion for injectivity of homomorphism. If and only if the kernel is trivial. And then this here, phi is surjective if and only if its image is all of H. This is simply the definition of surjectivity, but I wrote it down here anyway, so that we have kernel and image in this one proposition. Okay, the proof of this proposition is left as an exercise to you on the next problem set. And this is actually a perfect exercise because it really shows you where you stand. Now, after we have gotten used, I hope, a little bit to the abstract reasoning and all this stuff here, and lesson 12, because for some of you those might be new notions, injectivity and surjectivity. So if you have already gained a solid understanding of this stuff, this should not be too hard. It's not trivial either, but it should be doable. So test your skills and how far along you are with abstract reasoning by really trying this before looking up the solution or looking at the solution video. This is going to be exercise number 1 on problem set 13. Now, 3 more definitions or words that are used when dealing with homomorphisms. If a homomorphism of groups, later on also rings and whatnot, is injective, it is called a monomorphism, meaning that only a single element at most can be hit by phi. No element in the codomain H gets hit twice or more by phi. I think this is where this mono comes from. Surjective homomorphism is called an epimorphism, and a bijective homomorphism, so both injective and surjective, is called an isomorphism. And this is going to be a very, very important notion for the rest of this course. So get used to these 3 new words here, but the concepts should already be clear from lesson 12, injective, surjective and bijective. Okay, let's take a look at some examples. I use exactly the examples from lesson 11, that's why I call them example 1', 2', and so on. So, we take a look at the trivial homomorphism from G to H, which simply sends all the elements of G to the neutral element of H. So, by definition, the kernel consists of all the elements that get sent to E sub H, but those are all. So the trivial homomorphism has all of G as its kernel. And here, do not write this because G already is a set. All right? So do not confuse the notation here. And the image is a singleton set consisting only of the neutral element, the identity of H. Sometimes it is written like that if you're being lazy, but correct would be this here. Here it's okay to say, well, of course, I mean the set consisting of EH, but for a beginner I think it's better to stick to perfect notation. And here you cannot write these, or you shouldn't write these brackets here. All right, next example. We look at the projection from the integers to the integers mod n, sending an integer to its residue class, mod n, or the equivalence class, here denoted by this. I think I didn't use the sub n in the videos where I introduced that, would have been better. But if it's clear which n we are talking about, we simply write k overline or k bar. So what is the kernel? So by definition, the kernel consists of all elements that get sent to the neutral element. But here we have additive notation, so the neutral element is the residue class of 0 here, and this simply is pi n of k here. Pi n of k is k bar, so we are looking for all the integers that get mapped to 0, meaning that they are equivalent or congruent to 0, mod n, but those are exactly the integer multiples of n. So, for short, the kernel of this map is nz, meaning exactly that. 0 times n gives me that, 1 times n or minus 1 times n gives me that, 2 times n minus 2 times n, and so on. So nz is the kernel of this projection here. Okay, I think this should have been enough, but if you can't remember the definition of mod n, here it is even more explicit. K overline equals 0 overline. The residue classes are the same if and only if k is congruent to 0 mod n, but this means exactly that k is of the form 0 plus L times n, where L runs through the integers. So this is true if and only if k lies here in the integer multiples of n. So what is the image? Oh yeah, I forgot the new terms here. So this is clearly not a monomorphism, not injective, except for the trivial case where G is the trivial group consisting only of one element. Then, of course, the trivial homomorphism here is injective. And it is clearly not surjective, so not an epimorphism. That's probably not on camera, except for the trivial case when H is the trivial group. So this is an example of a homomorphism that is neither a monomorphism nor an epimorphism except for the trivial cases. This here is no monomorphism. It's not injective, clearly, because the kernel is not trivial, except for the trivial case where n is 0, but we do not talk about that. Now what is the image? Clearly all the elements here are hit by pi n, because I project every integer to its residue class, so clearly I end up with all the residue classes. So The image of this here is this whole group, so it is an epimorphism. So here we have an example of an epimorphism that is not a monomorphism. The reason again here is simply that the residue class of any k, so any residue class, is clearly pi n of k, because it does nothing but map k to its residue class. So clearly it's surjective, so it's an epimorphism. So the last two examples, we take a look at the absolute value going from the complex numbers without zero, together with multiplication, this is clearly a group, to the positive real numbers, again with multiplication. We established in lesson 11 that this is really a homomorphism of groups when the complex number gets mapped to its absolute value, or I think it's called modulus. I've never gotten used to this term. Okay, so what is the kernel of this homomorphism? By definition here, all the complex numbers without zero that get mapped to the neutral element here, but this is the number 1, the real number 1. Those are exactly the complex numbers of modulus 1, so all of the unit circle in the complex plane is the kernel. So this is sometimes written as 1, the unit sphere in the complex numbers. This is the kernel, so clearly this is not an injective map, so no monomorphism, because all these complex arrows here have length 1, so they all get mapped to 1. Clearly it is an epimorphism, because what is the absolute value of this complex number? It is simply r, the length of this arrow here. And this is true for any positive number r. So any r here has a pre-image under absolute value, namely this complex number for an arbitrary value of theta. So it would actually suffice to simply take the numbers, the complex numbers lying on the real axis. So again, we have an epimorphism that is no monomorphism. Last example, the determinant from the general linear group over a field F to the multiplicative group of F. We established the homomorphism property, that's nothing but the determinant multiplication property or theorem. So what is the kernel? By definition, it consists of all the matrices here that get mapped to the neutral element or the identity of this group, which is the field element 1. And this, by definition, here is the so-called special linear group of n by n matrices over this field, all the invertible matrices with determinant 1. In some problem set, you need to show that this is a subgroup of this. Now with this proposition here, this follows again because it's the kernel of a homomorphism. So this is always an elegant way to prove that something is a subgroup if you know that it's the kernel of some suitable homomorphism. Okay, now what is the image? I claim the image is exactly f star, f without a zero, so we would have an epimorphism that is no monomorphism. Again, always excluding the trivial cases, in this case the 1 by 1 matrices with determinant 1, this would simply be the number 1. So in this case it would be monomorphism. So why would this be true? Because if I have any non-zero element of f star, the multiplicative group of the field, then this matrix here clearly has determinant lambda. Okay, this is an invertible matrix. If lambda is not 0, having lambda as a determinant, and this exactly means that lambda lies in the image of det. So we have surjectivity. All right, that's already it for lesson 13. And as I promised, problem set 13 is not going to be over the top and out of control, but consists of a few nice friendly exercises so that you can get acquainted with these new notions of kernel and image of a homomorphism. All right, hope to see you in the solution videos or in next week's lesson. Until then, bye-bye.